So today we will be discussing different solutions to the critical section problem. So last time we introduced the critical section problem, and today we will be discussing some solutions to this problem. So who can remind us of the critical section problem? What do we mean by the critical section problem?
You have a section of code that you want to run to completion before another process can run it.
Another process that is what? Any other process in the system?
No, any other.
Okay. So you're saying it right, except that you're not specifying which other processes you don't want.
It's children.
No, not necessarily children. Yeah.
Could it be data-dependent processes?
Well, processes that are trying to access or that are trying to modify the same shared variable. So if you have a process that's modifying a shared variable, so there is a shared variable x, and you're modifying this x. When you are modifying x, you don't want any other process to touch x until you are done, completely done with the modification. So you're not interested in locking all other processes in the system. You're only interested in locking the processes that are accessing the same shared variable. Okay. All right, so this is the critical section problem. So a section of code that modifies a shared variable should be treated very carefully. We want to make sure that the modification of shared variables is done atomically. Now, in any solution to the critical section problem, we would like to see an entry section where a process locks the critical section, an exit section where the process unlocks, releases the lock, and then a remainder section, which is the rest of the code that is not critical, that a process can execute without having to worry about synchronization. So last time we said that for any solution to the critical section problem, we would like that solution to satisfy three conditions. Mutual exclusion, which is the main condition, the essential condition, which is only one process can be in a critical section at any given point in time. Of course, in a critical section that is modifying the same shared variable. Okay. So we will see some examples, because there may be different critical sections, right? So there may be a process that is a critical section in which a process is modifying variable x, and a critical section in which a process is modifying variable y. So when you are modifying x, all what you care about is processes that are in critical sections that modify x. Progress, we want to make sure that this solution makes progress. It doesn't cause a dead end, a dead block. So progress means if there are some processes that are interested in accessing the critical section, we must select one of them, and we cannot delay the selection indefinitely. And the selection should not include processes that are in their remainder section. So the selection is made between processes that are interested in accessing the critical section. Okay. Bounded waiting means that if a process is waiting to enter the critical section, then there is a limit on the number of times other processes will access the critical section while a process is waiting. Now, in today's lecture, we will go through examples that will explain bounded waiting very well. We will explain it by showing a solution that satisfies bounded waiting and a solution that does not satisfy bounded waiting, and then it will become clear what we mean by bounded waiting. Yes?
Oh, what do you mean by remainder section?
The remainder section is just the rest of the code that is not critical. Yeah, so if you have an application that modifies a shared variable, then that section of the code that modifies the shared variable is the critical section, and the remainder section is the rest of the code. Okay. The critical section problem also appears within the operating system itself, because as we said, operating systems themselves or kernels are today multi-threaded. So most kernels are multi-threaded, and a kernel could be preemptive or non-preemptive. So what we mean by preemption, preemptive means it's preemption is what we have been describing as setting a limit on the time that a process gets on the CPU, and if that time limit or that time quantum expires, then the process will be preempted. So when we take the CPU from a process, or when the system takes the CPU from a process, that's preemption. So if you have a time limit, if you have a time quantum, then that's preemption. If a process is given the CPU, or a thread is given the CPU until it blocks or it releases the CPU, then that's non-preemptive. So the point here is that preemption is what causes the critical section problem. Because we have the critical section problem, the reason why we have a critical section problem is that a process may get interrupted in the middle of modifying a variable. But if there is no preemption, a process will not get interrupted in the middle, and we will not have a critical section problem. But why do we have preemption? We have preemption for responsiveness. So that's what what preemption gives us, and that's why preemption is the kind of scheduling that we focus on. Now we will study the first solution to the critical section problem, which is Peterson's solution. Now, Peterson's solution is not a solution that you can implement. In fact, it's a theoretical solution or an algorithmic description of a solution. We'll see in a minute why it cannot be implemented. But what's the value of it if it's not a practical solution? Why are we studying it? We're studying it because it's conceptually interesting, and it shows us how the three conditions for the critical section problem can be satisfied. So we can, after we describe the solution, we will see how it satisfies the three different conditions, which are mutual exclusion, progress, and bounded waiting. Now, this solution is going to work for two processes, I and J. Okay? And there are two shared variables. These are the variable turn, which is an integer that indicates whose turn it is now to access the critical section. So if turn equals I, then it's I's turn. If turn equals J, then it's J's turn. And flag is a flag indicating if a process is interested in the critical section. So if flag of I is true, then I is interested. If flag of J is true, then J is interested. Now the assumption is these variables, turn and flag, may be modified atomically. So we are guaranteed not to get interrupted in the middle of modifying any of them. And this is the condition that is hard to satisfy in practice. Well, this is the condition that makes Peterson's solution impractical. Okay, so here's the code on the I side, and here's the code on the J side. Now we have to get used to parallel programming, where two processes are executing the same code in parallel, but they may be executing different lines in this code. So one process may be here, the other process is here. Okay, so now we have to get used to parallel programming. Multiple processes executing the same code, and they can be on the same line or on different lines. And we have to account for all possibilities. Now, if I is the current process, so if on the I side, this is the code that we will have, and on the J side, this is what we will have. So this is just the same code, but with every I changed to J and every J changed to I. Now, how does this work? Well, this is the entry to the critical section. So this is the entry section, this is the exit section, this is the critical section. What does the entry section have in it? It has setting the flag to true. So I is saying I am interested in the critical section. Then it's saying turn equals J. So it's saying turn equals other. And this is a key step. Here it's saying I am yielding to the other process. Turn equals I'm yielding to the other, turn equals J, I'm yielding to the other process. And then I is going to check if flag of J equals true, which means the other process is interested, and turn is equal to the other process, then I'm going to wait. Okay. Well, so now it looks like, we're setting both the flag of J, we're setting flag of I to true, and we're setting turn to J. And if both conditions are true, this process will wait. Now, how will this protect the critical section? How will it ensure that there will be only one process in the critical section? Well, first of all, if one process is interested in the critical section and the other process is not interested, then we don't have a problem. Process I is interested, it's going to set flag to true, and then it's going to set turn to the other process, but then it will check on these. If the other process is not interested, then flag of J is going to be false, and this process will just go into the critical section because the other process is not interested at all. Now, what if both happen to be in their entry section at the same time? So what if process I does executes lines flag of I equals true, turn equals J, and then process I gets interrupted here. Now, if process I gets interrupted here, and process J executes this, so now process J is going to set flag of J to true, then it's going to set turn to I. Now, it's going to set turn to I. Now, if I gets the CPU again and executes this, will it access the critical section or not?
No, because turn is set to I.
Okay, and this is I. So it's going to wait if turn equals J, if turn equals other. So now turn will no longer be other, turn will be I, which means that if under this scenario, process I does this and this, then process J does this and this, and then process I checks on this condition, it will find that the condition is false, and it will enter the critical section. Okay, because basically when J, so the process that does this last is yielding to the other process. The process that does this first, it yields to the other process, but then the other process, if it executes this afterwards, it's going to yield. So the last process to execute this is going to yield to the process that executed this first. Okay? So this term is very important because it will ensure that a process will not enter the critical section when the other process is in the critical section. And it's, processes here are not being selfish. Now we will appreciate this, we'll appreciate the term when we look into other solutions that do not have this. Then we will appreciate this. Okay, so now this satisfies all the conditions. So any questions on this before we? Yeah.
So both of them have access to the turn variable. Wouldn't that make that piece of code critical?
Well, yeah. So it's critical, yes, but it's
The problem is not to
it's
solve it.
guaranteed. It's guaranteed to be atomic. So it's access to turn and flag of I. So this is the assumption. Access to turn and flag of I is guaranteed to be done atomically. Okay, so that's why this is a theoretical solution. Okay, if there is a mechanism that will guarantee that access to turn and flag of I is atomic, then this will work correctly. If not, then this will not work. Okay. Any questions on this? Okay. So now, to make sure that this, to see why this satisfies all the conditions. So obviously it satisfies the mutual exclusion because there is a turn and turn cannot be I and J at the same time. It's either I or J. If turn is I accesses the critical section. If it's J, J accesses the critical section. So mutual exclusion is easy. And progress is also obvious because when two processes are interested in the critical section, the process whose turn is to enter the critical section is going to be the process that will get into the critical section. And processes in their remainder section are not going to get selected because if a process is in the remainder section, then its flag is equal to false, which means that it's not interested. And when one of the processes is not interested, the other process can access the critical section without having to wait. Now, what about the bounded waiting? So bounded waiting is the one that we need to understand very well. So we can understand this by asking the question. If a process attempts to enter the critical section 2 times in a row, while the other process is waiting, will it be able to do that? Will a process be able to enter the critical section 2 times in a row while the other process is waiting? Yes or no? Well, let's see, let's trace it. So suppose that a process entered the critical section. Then after it's done with the critical section, it's going to set its flag to false. So it's going to say, I'm not interested. Then it's going to do its remainder section. Now this remainder section could be short or long. Now remember, with all of these synchronization problems, we can never make any assumption about the relative speed of the processes. So we cannot assume that by the time process I completes its remainder section, process J will have gotten the CPU and will have, if process J was waiting, will have gotten the CPU and will have found flag of I to be false. No. You cannot make any assumption about relative speed, and you cannot make any assumptions about the fairness of the scheduler. So the scheduler may not be fair. Meaning that process J is waiting. So suppose that process J is waiting here. Okay? So process J is waiting because process I is in the critical section. So at this point, process I is in the critical section, process J is waiting. Then while process J is waiting, it loses the CPU. So the last time it checked, flag of I was true and turn was equal to I. Okay, and it was waiting, but then it lost the CPU. For how long will it, will it lose the CPU? We don't know. So while this doesn't have the CPU, process I could have completed the critical section, executed this, completed the remainder section, and executed the second the second iteration in the loop. Now, when process I does the second iteration of the loop, it's going to set its flag to true, so it's going to say I'm interested. Then it's going to set turn to J. So this is where it yields to the other process. Now, all of this is happening. Process I has the CPU, and this process J still doesn't have the CPU. Now, when process I attempts to do this, it's going to find turn to be equal to J. So process I is going to wait. So even though process I is enjoying more CPU time, it's getting more CPU time, it's going to get stuck here because of this turn equals J is going to yield to the other process. And eventually, this process will get the CPU and it will check on this flag of I. Well, is I interested? Yes, I is interested, but turn is going to be equal to I. To J, sorry. So turn is going to be equal to J because this process set turn to J. And then this process will get enter the critical section. So with this solution, it will be impossible for a process to access the critical section 2 times in a row while another process is waiting. Of course, it can access the critical section 100 times in a row if the other process is not interested. But if the other process is waiting, a process can access the critical section only once while the other is waiting. And this is exactly what we mean by bounded waiting. If you are waiting, then you are guaranteed that the other process will not access the critical section more than once when you are waiting. Okay? So bounded waiting means there is a limit on the number of times that other processes will access the critical section. And this limit in this particular case is 1. The other process can access the critical section only once. So this is bounded waiting. Now, if we don't have bounded waiting, we will have starvation. Now, we'll see this in the next example. Any questions on Peterson's?